Okay, we're going to start with 7.2, and I've got to talk to you. We're going to be trying to solve some equations, and we're going to do this really simply with just this, what we call this property of equality of exponentials. So what happens when you have two exponentials equal to one another? So say you have a base with its variable exponent, and you have it equal to that same base, but just a different exponent. Well, if it's true that the left side equals that right side, then it must be true that x is equal to y. Okay, now that's kind of intuitive. I hope I can, you can convince yourself that that's true. But it's very powerful, okay? So, but what you want to remember is this base, this must agree. Okay, that's important. Okay, so this base is the same as this base. And then it's also true vice versa. And we're going to use the vice versa part of this later, but let's talk about the regular part. So, for an example, real quick, if I have 10 to the third is equal to 10 to the x plus 1, then it's true that 3 is equal to x plus 1, and I can solve for x and get x is equal to 2. And that's the solution. So it's very easy to just sort of remove the 10s, right? You can just worry about setting the exponents equal to one another. Alright, so why don't you try one of these? Maybe I better make it harder first. So let's go to another page. And let's show how things can get a little bit harder. This whole idea of common base. Okay, so what if you start out and it's not a common base? So the first thing you're going to have to do is change it to a common base first. So that might happen in a problem like this when you have 2 to the x is equal 4 to the 5th. Okay, I don't want to say x is 5 because that's not going to be right. Okay, I don't have the same base. But I can write this so it is in the same base and then use the rule. So how can I write this? Here's a base 2. So usually we're going to go to the simplest, smallest common base, which would be 2. So leave this left-hand side alone. Change your 4 to base 2 squared. So that's my 4. And that 4 is being raised to a 5th power. So now I have an exponent raised to an exponent, so that's multiplication. I have 2 to the 10th on that right-hand side. So now I can use my property of equality and say x is equal to 10. And that's my solution, okay? So now we ought to let you try one of these and see if you can change to a common base so that to use this property. So why don't we try thinking about 5 raised to the x power, that's an x, equals to 125 raised to the 1/2 power. Okay, and see if you can solve that. Pause it. Okay, and we're coming up with x is equal to 3/2. No problem, okay? Some of these powers, 5 cubed is 125, you're going to have to remember. Okay, I want to try some of these same kind of things, but using some of our negative exponents, because we're going to need a little more practice with those. So, what if you had something with, get my marker going, 3 to the x plus 1, but over here we have 1 over 27. We're going to do the same idea of trying to find that common base before we equate the exponents. So what can I do with the 1 over 27? I could call that 27 to the minus 1 power, right? So that's the trick we want to make sure we're good at. And then what can I call 27? I can call that 3 cubed. So that 27 there is raised to the minus 1. And of course an exponent raised to an exponent is multiplication. So 3 to the negative 3 is 3 to the x plus 1 because the left side didn't change. Now I have the same bases. Now I can equate those exponents. So x plus 1 is equal to a negative 3. So x is a negative 4. And that's my solution. Okay, so let me try another one for you to do. What if you had 2 raised to the 2x, and I set that equal to 1 over, 16, and see what happens there. Go ahead and pause it. Okay, hopefully you got x equal negative 2 as a solution. Now, I want to just point out you might not have done it in exactly the same sequence I did. I changed it up even from my example, because I changed 16 to 2 to the 4th first, and then I used my negative exponent. Or I could do those in any order. It didn't really matter. So either way is fine. Now I just want to point out some common errors, making sure we're using our order of correctly when we're evaluating these sort of exponential equations. You know, in typical, when we have exponential growth, we talked about n was equal to n naught, your initial value, times whatever that growth factor is, kind of thing, and raised to the exponent for usually time. Okay, so let's say we say it's been 5 days. Everything is tripling after 5 days. Oh no, triples every day, sorry. Triples each day, and it does that for 5 days. And you started with 100. Whatever it is. So bacteria, whatever you're counting, fruit flies, zombies. So let's go ahead and put this all in to make sure we can follow our order of ops. N is equal to 100 times, okay, there's a times there. You have the B is going to be a 3, and then the amount of time is 5 days. Okay. So that's the equation once I plug everything in, and I have to do this. And what I want to point out is order of operations says you have to do exponents first, okay? Some people are very tempted to multiply first, okay? They want to take 100 times 3, get 300, and take the 300 to the 5th power, but that would be wrong because you're not following the right order of operations. So the correct order of operations is 100, and 3 to the 5th, what is that? That's 81 times 3, 243. So, and then of course it would be 24300. So I would have that many fruit flies at the end of 5 days. Okay? So that goes on. I want to make sure you did that right. And then we want to be able to solve for B. So I'll start with my standard growth model. And let's say I have, our fruit flies again, doesn't matter. Let's say we have 1,280 fruit flies after 3 days when I started with 20. So my 20 fruit flies multiplied up to 1,280 fruit flies in just 3 days. So what can I say about how things are changing, right? Find the growth factor. So I'm going to stick everything in. 1,280 is equal to 20 times B to the 3. Alright, so to find B, I'm going to go ahead and divide both sides by 20, right? Because that's going to help me isolate, if you remember how to do radical equations kind of thing. Dividing by 20 gives me 64 is equal to B cubed. And how do I under a cube? I'm going to cube root both sides, right? So that gives me 4 is equal to B. And I'm done. Okay? So that works out for that. One of the favorite things we like to do is compound our money, like we did that penny. So let's take a look at that. Okay, one thing we really like to do with exponential growth is compound interest. And now, compound interest is different than just a simple interest where you put some money in and that money you put in earns interest and you're done. When you have compound interest, not only you put the money in, that money earns interest, but then you leave the interest that you earned stays in the account, okay, so that then you start calculating interest based on the original plus the already earned interest, okay? So you're calculating interest on interest as well. So that's the compounding part of it. And so as you can imagine, things grow even faster because you're earning interest on a bigger amount every time. So it's nice to have compound interest, and it goes like this. Let me give you the formula for this. Compound interest was called by Albert Einstein to be the most powerful force in the universe. He's a pretty smart guy. So it does kind of show you the importance, we talk about putting a little bit of money away. If you do it early enough when you're young, when you first get your job, then wow, that's going to compound for a long time and be very valuable when you retire. Maybe you can go to Maui or something. So let's talk about compound interest. We talk about the principal. Remember, the principal was the amount you invest. And in the past, we always just calculated how much the interest earned was, but now we're going to do a straight-up calculation to find the account balance. So this will be your original amount, your principal, plus how much you earned to give you your new account balance at the end of some amount of time, T, right? T time. We'll usually do that in years because we always do R is your interest rate as a yearly percentage. And what we're going to have is N, which is going to be the amount, or the number, let's call it a number for N, of compoundings that you have in a year. So are you compounding twice a year? Are you compounding quarterly? Are you compounding every month, every day, every week? How often are you compounding? Okay. So the formula goes like this. You have your account balance A is equal to what you start with times this growth factor, which is 1 plus R over N. So you have the growth factor is your percentage, the 1 plus, right? We always have that. The percentage now is divided by N, okay? So that's the number of compoundings a year. But then you're going to raise it, make up for that N in the denominator by raising it to an NT. Okay? So that makes for compound interest. So I want to go ahead and do a quick calculation so you see how this works. If you start with $100 and you do this for 20 years at 1.2%, and you do it twice a month, could you figure out how much money you would have in your account? What is your account balance at the end of that 20 years? So first of all, let's go back and talk about this twice a month compounding. So if you're doing it twice a month, then N is equal to 24. Okay? So let's go over here and calculate this really quick. My account balance would be 100. 1 plus 0.012. Okay, that's R, where I've adjusted the percentage, over N, which is 24. And I'm going to raise that to the 24 times, how many years was I going? 20 years. Wow. So that's going to be a huge exponent, okay? So let's look at this. A is equal to 100. I don't have a calculator. Hold on. Okay, let's see if I can do this. This is 1.0005 or something like that. That's barely bigger than 1, okay? So each compounding, because you're doing it 24 times in a year, each one isn't much, okay? But you're doing it a lot of times. So that's the growth factor. But look how many different compoundings you have. You have 480 compoundings to do. So now I have to take this 1.0005. Remember, I'm going to take my exponents first. Let me try that. Okay, so that gives me 100. Oh, I'm going to forget it. It was on the other screen. I think it was like 1.27. Okay, and then of course when I work on that I get 127. So I have $127 is my account balance after 20 years when I left it sitting in there forever and ever. Okay, better than simple interest, I promise you. Compounding, and the more compoundings you have, the better. You'll get more money in the end.